So we're going to look at 4.2, part 1, but there's something we have to look at first that's going to be in 4.2. And I'm going to show you an example, do something on the calculator, and then it's a pretty easy concept. So let's graph this. 2x cubed minus 7x squared minus 8x plus 16. Okay, I'm going to put that in y1. And then in y2, I want to graph just 2x cubed. And I just want to compare the two. Okay, so we've got 2x cubed minus 7x squared minus 8x plus 16. And then in y2, I'm going to put 2x cubed. Now, I'm going to set a certain window. Okay, that I want to look at this. Let's do a window from -8 to 8 on the x-axis. So let's go -8 to 8. And let's go from -40 to 40. Let's start with -100 to 100. Yeah, let's do that. -100 to 100. Okay, so there's your window. All right, let's graph it and let's see what they look like. Okay, so there's the first one. That's the y1. And here's the y2. Okay. Do they look the same? No. I think if you look at them in that window, they definitely look different. All right. Let's zoom out a little bit. Let's try doing -40 to 40 on the x. And let's try -10,000 to 10,000 on the y. Okay, so this is a lot more zoomed out. It's a lot more zoomed out. And I'm going to graph them again, and then I'm going to ask the same question. How do they compare to each other? They're still the same graphs. All I'm doing is zooming out. Okay, so there's the first one zoomed out. And there's the second one. How do these two graphs compare to each other now?
They look similar.
They look, yeah, very similar. In fact, if you zoom out a little bit more, maybe even we could make them look exactly the same. So this idea that you can zoom out enough and two graphs can look the same, it has to do with this term right there. That first term, 2x cubed, basically controls what this graph is going to look like. This minus 7x squared minus 8x plus 16, when you zoom out enough, this part has really no effect on the picture at all. Because cubing something is way more powerful than squaring it as you start to get bigger and bigger and bigger. So this term right here, 2x cubed, is called an end behavior model. EBM. Okay, end behavior model. The end behavior model is the term with the biggest exponent in a polynomial. And the idea of an end behavior model is that if you graph the end behavior model and you graph the entire original polynomial and you zoom out enough, the end behavior model will look exactly the same as that more complicated polynomial. That's the idea of an end behavior model. The EBM captures the big picture of what it's going to look like. Any question on that idea? So what would be the what would be the EBM of this? 8x squared minus 5x plus 6.
8x squared.
8x squared. If you graph 8x squared and then you graph this original in the same window and you zoom out enough, they're going to look exactly the same. So this is called the end behavior model. Right, that's the only thing we had to know going into this section. All right, so now let's see if we can get through the first half of 4.2. So when you have a rational function, okay, something like, let's say, x squared plus 3 over x minus 1, x plus 7. Does it look like the numerator and denominator have a common factor there? No, they don't. And if the numerator and denominator don't have a common factor, what would happen at 1 and negative 7? You would get a what on your graph? We talked about this kind of dotted line yesterday. Yeah?
That's true.
A what?
That's true.
Yeah, you get a vertical, specifically a vertical asymptote. So 1 and negative 7 would give you vertical asymptotes in this graph. What if you did have a common factor? Let's say you graph x minus 2 over x minus 2, x plus 3. You're going to get a vertical asymptote at negative 3. But at 2, you're not going to get a vertical asymptote. You're going to have a
Horizontal.
not a horizontal asymptote. This is something different. Something you can't see on the graph. A hole, yes. A hole, fancy word for that, is something that's disconnected. Think of a hole as like something you have to jump over. It's a disconnect. So if the numerator and the denominator have a common factor, like in this one, you might get a hole that you can't notice on the screen. So the only way you would know that the hole is there is if you go back to the original problem and check, do I have a common factor in the top and in the bottom? And the answer to the one that I circled is yes, you do. So you would end up with a hole in the graph. If you don't have common factors, that's when you get the vertical asymptote. If you do have common factors, hole. I'll just put that in parentheses. Hole. No matter how much you zoom in, you'll never see the hole. It's infinitely small. You can't zoom in and see it. Right, so let's try a graph. But I want you to tell me, first of all, what number are you not allowed to plug in for x here? 1. Is it going to be a hole in the graph at 1 or a vertical asymptote in the graph? Yeah, hole. This one's going to be a hole. Because if you graph x minus 1 divided by x minus 1, I meant to get rid of the other one. And let's do zoom 6. You're basically dividing two things that are the same. So they cancel each other out and you get 1. Looks like a solid line. But we know that you can't plug in, what number again? 1. So what you should do, you should almost erase that part that's right there and draw it as a hole. So it should look like this. That's how you show there's a hole in the graph. How about this one? X minus 1 squared divided by x minus 1. Is there a value we can't plug in for x? Yeah?
1.
1. You can't plug in 1 again. Now, same question. Are you going to have a hole in the graph at 1 or a vertical asymptote? What do you think?
Is it vertical asymptote?
Well, what does this mean? X minus 1 squared. If you wrote that out,
X minus 1 times X minus 1.
right, it means X minus 1 times X minus 1 over X minus 1. Do the numerator and denominator have a common factor?
Yes.
They do. So that means you're going to get
A hole.
a hole in the graph. So if you type in this one, I just need to insert an exponent of 2. Not going to see any vertical asymptote. But when you get to 1, there should be a hole right there. And if I press trace and I try to go to the number 1, it doesn't even write anything at y because it can't. There's no value. Normally when you hit trace and you type in a number, it gives you a number for y. But when I go to 1, I can't do it because there's a hole. Okay, so in both of those examples, there were no vertical asymptotes. Okay, we had what we call, this is the fancy name for a hole in a graph, it's called a removable discontinuity. That's another name for a hole. It's a removable discontinuity. Discontinuity just means not connected. And a hole makes the graph not connected. There's like a break in it. Yes.
Then why is it removable?
Think of it as removable because if you have a small, it's almost like you could fill it in easily. That's what it means, right? It's a very, very small hole. So all you have to do is put a little dirt in it and you could fill it in. Versus if you had something like this, and now it's connected. Do you agree once I fill it in, it's connected? So that easily made it connected. Now, if you had something like this, and then something like this. Would it be easy to just fill in a little spot and then make these two connected?
No.
If we zoom out far enough.
Well, even if you zoomed out, this piece is still just going to keep heading up forever, and this piece is still just going to keep heading over forever. So is there any way to fill something in and make those two connected? No. So this is a discontinuity, but it's not considered removable because you can't just fill something in real quick and make it all connected. Okay. I wasn't really going to get into that, but that's why. Okay. So any question on that name? Removable, that's a good question. Any question on removable discontinuity? Okay. So we're going to do a problem like this in a second. We're going to have a polynomial in the top and another polynomial in the bottom. That's what this represents. Just a polynomial in the top and another polynomial in the bottom. So maybe it's like 8x cubed plus 2x squared plus 3x plus 6. The last term is your constant. And then each term has the exponent drop as it goes to the right. Cube, squared, and I don't know how many you would have, however many you have. Okay, and then maybe in the bottom you'd have something like, I don't know, 5x to the 4th plus 3x cubed minus 8x squared plus 6x plus 2. Just made that up. But that's an example of what you'll actually have in a real problem. We just talked about how to find an end behavior model. What would the end behavior model be for something like this? Yep.
8x cubed.
Right. It's the highest term. What would the end behavior model be for this top one? Well, I guess I like 8x cubed. Huh? What would the end behavior model be for that bottom?
5x.
5x to the 4th. Now, what would the end behavior model be for that one I just put a box around?
And x to the power of n.
Yeah. Would be what I just highlighted right here. That's the end behavior model of what's in the top. What's the end behavior model of what's in the bottom.
BMX to the power of n.
Yeah, that's the end behavior model of what's in the bottom. To find the end behavior model of this whole thing, we divide those two. Okay, so you find the end behavior model of what's in the top, what's in the bottom, and then you divide them. So if we were doing the ones that I have, the top is 8x cubed, and the bottom is 5x to the 4th. And when you simplify that, that's the end behavior model for this whole fraction. You just take the one in the top, divide by the one in the bottom. Now, 8 and 5, does that reduce when you try to divide 5 by 8? No. This does reduce. And if you don't remember how to reduce it, I'll show you right now. Okay. So, a sub n x to the n is the end behavior model for the top. That's what I highlighted in yellow. Bm x to the m is the end behavior model for the bottom. And the end behavior model for f of x is when you divide the two. That's the top one. That's the bottom one.
Compare that.
Yeah. Now, does anyone remember the rule when you have two things you're dividing and they have the same base, what you do with the exponents?
Doesn't the result stay with the larger exponent?
The result stays with the larger exponent, yeah. So in this case, in the bottom.
Yep. So that would be -1 in the denominator, right? Because you're subtracting 3.
So in the top, we have 3 x's, right?
Yeah.
In the bottom, we have 4. How many x's can I cancel from the top and the bottom?
3.
3. Those are gone. Those are gone. Well, there's got to be something left in the top.
So it's just
We got, what do we put there?
1.
1. And what's in the bottom?
x.
X. So the result ends up in the bottom. So in that case, it would be 1 over x. So the pattern in general is, if you can, you divide the two numbers that are in front. With an 8 and a 5, I can't do that. So I would just have to leave it as 8 and 5. And then you subtract the exponents. Right, if you get confused, if you forget that you need to subtract the exponents, because sometimes subtracting exponents can lead to a negative number. A negative number just means the answer goes in the bottom. Because if you subtract here, what's 3 minus 4? -1. That means the answer goes in the bottom. If you had something like this, let's say x to the 4th divided by x cubed. What's 4 minus 3?
1.
+1. That means the answer would go in the top because the exponent is a positive. Right, so negative exponent, if you do that, just means the answer goes in the bottom. Okay, and that's the end behavior model for a rational function. All right, we'll try another one of those. And then I'll tell you, what does the EDM really, what does it do for you? I'll tell you what it does. Okay, so here's one. It says find the EDM and then find the horizontal asymptotes. There's definitely a connection between those two things. All right. You know what, I'm not even going to put an equal sign. I'm going to put an arrow. Because the EDM is not equal to the original problem. It's a simplified version of the original problem. What's the EDM of what's in the top? Yep.
2x squared.
Yep, 2x squared. What's the EDM of what's in the bottom?
3x cubed.
3x cubed. And now when we simplify that, How many x's can I cancel from the top and the bottom?
2.
I can cancel 2. And where would I would have how many x's left over? 1, and it would be in the bottom. So this would be 2 over x. That's your EBM. If you forget how to do it, you can always just write it out the long way. And then say, all right, I got 2 in the top, I got 3 in the bottom. I can cancel 2 here and 2 here. Got my 3. Sorry about that. And you're left with 2 over 3x. Now, if this was 2 over 4, I would have reduced it. But I can't because it's 2 and a 3. That's your EBM. Okay. Any question on finding the EBM? Now, the next thing they want is the horizontal asymptote. How does the equation of a horizontal line always start? It's what letter equals?
Y.
Y equals. Okay, when I write HA, that's horizontal asymptote. Now, to find a horizontal asymptote, you look at what happens as you head further and further and further to the right or to the left. What happens in a graph? If you head further and further and further to the right, what's happening to the x value? It's increasing, and what is it increasing towards if you just keep heading to the right? Infinity. And what about if you just head to the left?
Negative infinity.
Right. So to find a horizontal asymptote, normally you would look at the picture and see what happens as x heads further and further to the right, okay, as x gets bigger and bigger. Well, we don't really need a picture if we have an EBM. We can look at this. As x heads further and further to the right, it's going to get bigger and bigger and bigger. So imagine plugging in a really big number for x right there. All right, let's say we're at like 1 million. What's 3 times 1 million? 3 million. And if you take 2 and divide it by 3 million, what kind of number do you get?
Pretty small.
Pretty small. Pretty close to what number?
0.
0. That's your horizontal asymptote. So once you have your EDM, just imagine plugging in a really huge number for x. Even like, 1,000, that would work. If you plug in 1,000, you'd be way to the right. That'd be 2 divided by 3,000. That's an extremely small number. Will it ever, what's that? Will it ever reach 0?
No.
No, even if you take 2 and you divide by 50 billion, 2 divided by 50 billion isn't 0. It's very, very small, but not 0. Any question on how we use the EBM to find the horizontal asymptote? Just let x be a really big number, and that's your horizontal asymptote. Kind of a hint, anytime you have an x in the bottom and you only have a number in the top, it's always going to be 0. Anytime the x is in the bottom by itself. All right, let's try this one. Okay, what's the highest degree term in the top?
2x to the power.
2x
Power 4.
to the power 4.
And let's say that.
And what about the denominator? What's the highest degree term there?
3x to the power 4.
No.
I'm going to agree.
Okay. Now, you don't want to leave the EBM like that. You want to simplify it. So, what cancels out here?
X4 and X1.
Yeah, you have 4 x's in the top, 4 x's in the bottom. They all cancel out. And what are you left with for an EBM?
2 over 3.
2 over 3. So it is possible that the EBM doesn't have a letter in it. It's just 2/3. Now, I'm going to ask the same question I asked last time. We looked at what happened as we let x get bigger and bigger in the EBM, and that was the horizontal asymptote. So look at your EBM. What happens as you let x get bigger and bigger and bigger to what's in that box?
It's just going to be 2/3.
It's just going to be 2/3 because there is no x. So in this case, the horizontal asymptote is 2/3. Every horizontal asymptote in tonight's homework is going to be one of two things. If you end up with an x in the bottom, it's going to be 0. If you end up with all the x's canceling, it's going to be whatever these numbers were right there. But those x's can only cancel if these two exponents are the same. That's when they cancel. This other stuff doesn't even matter. Doesn't make a difference for what we're doing. Okay. Any question on that? Alright, so there isn't that much more. There's just a couple examples left. So now we're going to look at how we can sketch the graph of a rational function. This is what we'll spend the rest of most of 4.2 doing. Today, we are only going to look at the example where the degree of the numerator is less than or equal to the degree of the denominator. So in example 2a, the degree of the numerator was a 2. The degree of the denominator was a 3. The degree of the numerator was smaller. In example 2b, the degree of the numerator was how much? What was the degree of the numerator in 2b? Yeah.
Numerator is x to the power 4.
So what's the degree?
The degree would be 4.
4. And what was the degree of the denominator?
4.
4. So we looked at an example where the degrees were equal, and the top one, the degree of the top, was less than the degree of the bottom. That's the kind of examples we're going to look at right now. One of these two. All right, how do you sketch the graph? Well, sketching the graph of a rational function, it's not quite as simple as like a straight line. These graphs have asymptotes in them, or curve. Sometimes they curve too. So I'm going to give you some hints at what we can do. One thing that can be helpful when you're sketching any kind of graph is to figure out where it crosses the x and the y-axis. To figure out, and this might be kind of the opposite of what you think, but to figure out where it crosses the x-axis, you plug in 0 for y. To figure out where it crosses the y-axis, you plug in a 0 for x. Not every graph crosses an axis. So that may not work. Okay, but if we can do it, we'll try to figure out where it crosses the axis. Right? That gives us at least a point. The next thing we want to do is start sketching our asymptotes. Usually when you do these problems, you're going to have a vertical and you're going to have a horizontal. And what that does is it gives us kind of a grid that helps us to sketch the picture. So remember from yesterday, vertical asymptotes are where the denominator would equal 0. I don't think you're going to have to worry about holes too much in this section. Mostly they're going to be asymptotes. The other asymptote we need is the horizontal. The quick way to find the horizontal asymptote is to find the EBM and then let x be what kind of number? Yeah?
0.
No.
Really large.
Really large. Remember I gave you guys an example of plugging in like 3 million? Let x be a really large number if you even have an x to fill in for. Okay. let x be a really large number.
So there's always the possibility that the EBM and horizontal asymptote would be the same.
They could be if there's no letter, yes. Yep. Now, this we're going to use the graphing calculator for. Let's say we had a vertical asymptote of 2. Well, you can't plug in 2, because that would cause you to divide by 0. But you could plug in something close to 2. What would be a number really close to 2?
1.9.
Even closer.
1.9.
Okay, that's good. So 1.999. That's a really close number to 2. What's another number that's really close to 2 besides 1.99?
2.0.
Yeah, 2.01, 2.001, something really, really close. So once we get a number that's a vertical asymptote, we're going to check a number on each side of that asymptote. I guarantee what's going to happen every time is when you plug in a number on one side, you're going to get a really big answer. When you plug in a number on the other side, a really small answer. Like I'm talking big approaching infinity and small approaching negative infinity. Because all of these graphs usually do something like this. Curves up, and then the other part curves down. And here's your asymptote. So one side is up really, really high, and the other side is down very low. All right, so we'll find our intercepts, sketch the asymptotes, use the graphing calculator to help us. And step 5 is really just double checking it with the calculator. Okay, any questions on those 5 steps before we try a couple examples? So the calculator is going to be really important here, okay, to help us. Okay, so there's the one that we're going to do. It says to sketch a complete graph of x minus 1 over x squared minus x minus 6. Okay, let's start by seeing if we can find our intercepts. Now, f of x is just another name for what letter?
Y.
It's just another name for y. So if you like to write y equals, you can do that. Or just leave it as f of x. Fine. Let's start by finding x-intercept. To find the x-intercept, it says to let what letter equal 0?
Y.
Y. Yep. So let's let y equal 0. So you fill in a 0 on this side. 0 equals x minus 1. Now, there's only one way that a fraction can ever equal 0. How can you divide two numbers and have the answer come out to 0?
0 would be the numerator.
0 would have to be in the numerator, yes. So what would you have to plug in right here
1.
for 0 to be in the numerator? Yeah, 1. So the x-intercept is basically when the numerator is 0. Doesn't matter about the denominator. So your x-intercept is at 1. And that's a point on our graph. Okay. What's the other intercept we can find?
Y.
Yeah, you can find the y-intercept. So this is when y equals 0. The y-intercept is when x equals 0. Let's plug in 0 for x and see what we get. Well, in the top, what's 0 minus 1?
Negative 1.
Negative 1. And if you plug 0 in the bottom, what's 0 squared?
0.
Minus 0?
0.
Minus 6.
Negative 6.
Okay. So my y-intercept is at 1/6. So basically it crosses just above the origin. Those points are so close together that's not really super helpful, but that's okay. So we got our intercepts. The next thing it says to find is the vertical asymptotes. That's where the denominator would be 0. Well, I have a hard time looking at that because it's a quadratic. What's something we can do to a quadratic that makes it easier to see the zeros? Simplify it by taking it and factoring. Yep. Let's factor the bottom. Okay. How does the bottom... Well, let's just start with the first two terms. What's going to be the first term in each parenthesis when we factor? Yep. And we have a negative middle and a positive at the end. So what does that mean my signs have to be?
Negative, positive.
Yep, you're going to need one of each. Now you need two numbers that multiply to give you 6.
2 and 3.
2 and 3. And I would try them exactly in that order. That's going to give you minus 3x plus 2x. Perfect. That is how you factor it. Now, what number would you plug in here to get 0? Negative 2. So vertical asymptotes, negative 2. And what number would you plug in here?
3.
3. So there are 2 vertical asymptotes in this graph. Negative 2 and positive 3. What I'm going to do now is draw a dotted line in. I'm going to zoom out so I can do it a little easier. Okay, I want it at negative 2. And I want it at positive 3. I think that'll be okay. Yeah, that looks great. Okay, so I got my vertical asymptotes. And now the EBM. Okay. That's going to give us the horizontal. Okay, what's the highest degree term in the top?
X.
X. What's the highest degree term in the bottom? It helps to look back at the one that's all foiled together.
X squared.
X squared. And what do you get if you simplify that?
1 over X.
1 over X. Good. Now, let X be what kind of number? Really big or really small?
Really big.
Really big. What happens if you let X be a really big number? What are you going to get closer and closer to?
0.
Anytime it's an X in the bottom, it's 0. Okay, so now put a horizontal line at 0. It's not that good. That's good. Okay. When we sketch it, we usually end up drawing 3 pieces. That's what this kind of graph looks like. It's going to be in three pieces. What we want to do now is get some more points near the asymptotes. Let's start with this one. What number is that asymptote on the left at?
2.
It's at negative 2. So let's type it in, and then we're going to go to the table, and we're going to put in a number close to negative 2. So it's, I can't see it, x minus 1. I'm going to divide by, and I would put it in parentheses, x squared minus x minus 6. Don't even need to graph it. I'm just going to use the table. Now my table is not letting me type anything in. So to be able to type something in on the table, I think I said it yesterday.
Mm-hmm.
Anybody remember what you have to go to?
Second window,
Window.
and
Yeah.
then go to ask.
That one's got to be on ask. Mine resets every time. Yours shouldn't. Okay, so you have to set it like that. Now I can type in whatever I want. Don't put negative 2. And don't do positive 3. Those are the asymptotes. So we're going to get an error. But what's a number that's pretty close to negative 2? Maybe just a little smaller.
2.99. Oh, 2 point. Oh, close to 2.
Negative 2. Negative 2.
Negative 2.01.
Yeah. Negative 2.01. And when you plug in negative 2.01, you're down at negative 600. So basically, you're way down. Right. Now let's try a value a little bigger than negative 2.
Negative 1.99.
Negative 1.99.
Negative 1.5.
When you plug in negative 1.99, you're way up at 60. Okay, so now, you're way up here. You're always going to end up on one side being very low, and on the other side it's going to be up really high. Now let's do the same thing for this one. What's the other vertical asymptote at? What number?
3.
3. What's a little bit smaller than 3?
2.99.
All right, so 2.99. We're at negative 40. And if you went even closer, now you're at negative 40,000. Just scientific notation. So the point is, when you're at just before the number 3, you're way down. And where do you think you're going to be just after the number 3?
Way up.
You're going to be way up. Now, if you want to get another point, I can go up to 10. So we could plug in 10 and just see kind of where we're at. We're at just above 0. Okay, 0.1. So right about there. And I could also do negative 10. That's as far as my graph goes. Negative 10. I'm at negative 0.1, which is just below 0. Right about there. Okay, so now we just have to connect the dots. Remember, you have to stay very close to the asymptote as you head left and right. So this has to basically stay right up against it. And it wants to keep going to the right, but it can't because it runs into that vertical dotted line. So what it's going to have to do is it's going to have to all of a sudden bend down and then stay closer and closer to that other one. It's kind of like a mirror image what's going to happen in the upper right. We've got to stay very close to that asymptote. And we have to stay very close to that one. And the two have to connect. So it's going to kind of curve down like that. Now the part in the middle, it has to go through all 4 of those points. So what kind of shape do you think we're going to get in the middle?
Backwards S.
Yeah, it's kind of like an S shape. It's going to stay really close to that. It's going to curve through those points. And then it's going to come down, getting closer and closer like that. It takes a little practice. And I might not have the curve perfect in the middle, but it's going to be pretty close to that. There's the left piece. There's the middle. And there's the right piece. Yeah, that's how you do it. So the asymptotes really help a lot because they give you sections to put your graph in. All right, any question on that one? That's about as hard of one as we do. Like that.
I got a question.
Mm-hmm.
It passes, I noticed it passes in the middle, the 0 horizontal asymptote.
Mm-hmm.
Is there like a hole somewhere? Because asymptote, I know sometimes they'll allow to pass them, sometimes they don't.
No, these pieces are all independently connected. Like you can draw the left piece without ever lifting your pencil, the middle piece, and the right piece. There's no hole in the middle one. No. There's no hole because there's no common factors in the numerator and denominator. X minus 1, x plus 2, x plus 3. They're all different factors.
So it does pass the asymptote.
Yes, it does. Passing the asymptote is perfectly fine near the origin. Where you don't want to pass the asymptote is as if you head to the right forever, or you head left forever. But right in here, it's perfectly fine. All right, so that was one where the degree in the top was smaller than the degree in the bottom. Okay, the top was a 1, the bottom was a 2. Let's try this one. So this will be our last one. And this is where the degrees are the same. First thing I would do, even if you're not looking at all the stuff you got to figure out yet, I would just factor the bottom, because you're always going to have to factor the bottom. In this case, does anybody see what you can factor out of both?
X.
Yeah, this isn't the kind of factoring we did in the last one. This is just a GCF. If you factor an x out, what would that leave you with in parentheses?
2x minus 5.
Yep, 2x minus 5. All right, and I'm not saying you have to find that intercepts every time, like the x-intercept, the y-intercept. Like, I don't know if I would do the y-intercept this time, because that means I have to put 0 on this side. And last time it was easy, because all you had to do was figure out what made the top 0. It was a 1. It's not as easy to figure out what would make the top 0 this time. So I'm going to hold off on figuring out the x-intercept. Okay, I'm not going to do it. I am going to do the y-intercept. So the y-intercept, I'm going to skip that one, is when you plug in 0 for x. That's usually an easy one to do. So if you plug in 0 for x, what's 0 squared?
0.
Times 3?
0.
Plus 0?
0.
Minus 4.
Negative 4.
Okay, so the top is negative 4. Now watch what happens in the bottom. What's 0 squared? Times 2?
0.
So that's 0. What's 5 times 0?
0.
What's 0 minus 0?
0.
So now we have that. What's wrong with that?
Can't do that.
Can't divide by 0? This graph never crosses the y-axis. It's never going to cross it. So y-intercept? None. So the intercepts don't really help too much in this one. So we're going to go back to finding the asymptotes. Okay, vertical asymptotes. That's what would make the denominator 0. What could you plug in here that would make that factor 0? 0. And how about there?
2.5.
Yeah, I would think of it as 2.5. That's an easy way to do that thing. So there's our verticals. I didn't write a spot for the EBM, so I'll just do it under this. Okay, what's the highest degree term in the top?
3x squared.
3x squared. What's the highest degree term in the bottom?
2x squared.
2x squared. And what happens there?
X squared cancels out.
X squared cancels out. And there's your EBM. So now this is the thing that what happens if you let x get bigger and bigger to the number in that box?
So we're going to go 3 halves.
It just stays at 3 halves. So your horizontal asymptote is at 3 divided by 2, or 1.5. All right, let's draw all those asymptotes, and then we use the calculator. So we got one at 1.5. Put that one in. Close enough. We got another vertical at 0 and 2.5. Let me zoom out. 0, 2.5. Just makes it easier for me to do it. All right. And now let's just check some points using the calculator. I'd say usually like 5 or so is enough to do it. But to get the points, you got to type it in. Can someone remind me, what was the numerator?
3x squared plus x minus 4.
Plus x minus 4. And what was the denominator?
2x squared minus 5x.
2x squared minus 5x. Okay. First asymptote is at 0. What's a number that's just a little smaller than 0?
Negative
0.0001.
001. If you go just to the left, you're down at negative 8,000. So you're way down here. And if you go just to the right of it, 0.001, you're up at positive 8,000. So now you're way up there. That's as good as I can do for positive 8,000. Just way up high. Okay, our next vertical asymptote was 2.5. What's a number that's a little smaller than 2.5?
2.499.
Yeah, 2.499. You're at negative 3,448. So you're going to be way down here. And where do you think you're going to be on the other side?
Yeah, all the way.
All the way up. Now, I like to check the edge of my graph, like 10 and negative 10. At 10, I'm at 2.04. So that's like, be right about there. And then negative 10, I'm at 1.1. Okay, so 1, right about there. So I can kind of see what's happening here. It's going to stay really close. It's going to curve through that one. In this section, probably going to do something like that. The middle, I'm not sure. What's another good x value I could check that would be in the middle so I get another point in that spot?
1.
Yeah, we could check 1. 1, 0 is a point. Okay, we could check 2. Negative 5. So 2, 1, 2, 3, 4, 5. All right, I think that gives me enough. I can see what's going to happen now. I'm going to get a curve in the middle, but it's not going to turn quite as much. It's going to kind of do something like this. See those points? That's my guess. Okay, let's see. So there's the left. There's the middle. Notice it gets so steep in the middle it kind of gave up. It should just continue up forever. And yeah, everything there looks good. That actually is better than the calculator because it doesn't cut the graph off. Right, that's how you sketch rational functions. So tomorrow we'll do a little bit more with sketching. And then that'll be it for section 4.2. So homework, it's 1 through 5 odd, 9 through 11, 50.